Hi, my name is Nicola Hines, and today I'll just be doing the summary for my article, The Wave Aspect of Light Interference. And we're just going to be going over some of the theories surrounding light itself. One of that principle is the way light behaves. Okay, so one of the main, the first aspect or introduction to better understand light was to understand physics itself, because you're going to need that. The article talks a lot about physical quantities. Did you imagine working through difficult equations and formulas, and how these are applicable to science, and not just science but to our daily lives? We also learn that in order to better understand light, you have to understand physics, and that everything that we use right now in our lives, everything electronically, is a result of the principles that governs light and physics. So light again is invisible, and it's everywhere. Also talks about the groundbreaking technologies that we have over the past century. Giving credence to Albert Einstein, Galileo, Sir Isaac Newton, also Young for his double slits theory. So we do know that visible light is an electromagnetic wave that our eyes respond to. So they also have a range that was common throughout the text, from 380 to 760 nm. That's the range for light's visibility. That's what we see whenever light comes in contact with an object. The other part, so once you understand the principles of life, of light, you will now understand how light works. It does travel in a straight line, and light interacts differently with smaller objects than it does with larger objects. So Young's double slit experiment was also widely mentioned throughout the book. So basically what that experiment proved was that, when scientists asked the question, what is light? His experiment proved that light was a wave. And so for years, the people, concluded that light, the best way to describe light is that, hey, it's a wave. And that was conducted with a double slit, known as the double slit experiment, and proved that, when light was shown from one end of the beam or the slit to another, the particles were wave-like. And they also did travel in a straight line. And so a lot of scientists again concluded that that's what light was. And so, again, taking into consideration the laws of physics, understanding how interference would affect light itself, and also the force, and they did talk about gravity. It's hard to mention something scientific without mentioning Sir Isaac Newton. And so, take into consideration the laws of motion, and how gravity works on light, how speed, how motions, is light horizontal? Is it going to be vertical? How you measure it, depending on how you're going to look at light, from the left to the right, or you're going to look at it from the bottom. Then with that, we move on to, so Young's double slit experiment did conclude that light was a wave. Then we moved on to Einstein's experiment, which proved that light was a particle, because of the way light behaved. And also he discovered photons, that light would emit photons depending on where you shine it, how it is, and what you're looking at. So that actually refuted the experiment that was done by Young in 1801. There was a lot of quantum physics, a lot of quantum mechanics, and better understanding the wave packet in light itself. So after looking at both experiments, so scientists, after debating, do we go with Young or do we support Einstein's theory, they came up with a, advanced apparatus and mechanics to figure out what is light, and they a lot of quantum physics were taken into considerations, a lot of peer review, a lot of consultation, a lot of going back and forth to say, hey, we've got to tell the public what this is. We have to decide, is it a particle or is light a wave? So in order to better understand the dual nature of light, you have to take a look and say, so some of the properties of wave, diffraction, polarization, interference, reflection, and refraction. Some of the properties of particle also include reflection and refraction. And then the biggest thing that Einstein discovered was that because light is a particle, it cannot escape a black hole. So because light cannot escape a black hole, it interacts with gravity. And light, the other key element of light was that it has a photoelectric effect. But then when you combine the results from both experiments, you find that, hey, both of these have reflection and refraction. And then also the distinction between the wave-like characteristics and the particle characteristic. And so scientists had no choice really but to conclude that, hey, it is a wave and it is a property. It also is a particle. So when throughout the text we had to look at like light itself and all the discoveries. So in the mid 1600s, it was Newton that proposed that light consisted of particles. He was able to explain the phenomenon of reflection, like looking at light reflecting off an object or a mirror, and also refraction. And he used a color-coded particle to demonstrate this. Then we have Christian Wien in 1600, who proposed the alternative to that light consisted of waves. After that came Thomas Young in the 1800, who, thankfully to his double slit experiment, provided conclusive evidence that light was a wave. His double slit experiment proved that light beams interfere differently, that particles couldn't, that only waves could do that. And so then we have in the 1860, we have Maxwell stated that light was a wave. So Maxwell teamed up and sided with Young and said, hey, it's a wave. And then we have Einstein in 1905, who came along and explained the photoelectric effect by proposing that light behaves as if it were a particle, in that light energy is concentrated in particle-like photons. So we have Newton in the 1600s, we have Thomas Young in the 1800s, we have Maxwell in the 1860s, and then we have Einstein in 1905. But the article itself kept referencing, because of the dual nature and how mysterious light is. Hey, light is mysterious. It's undecided. One experiment will prove that it's a wave. Another experiment will prove that it's a particle. Light has wave characteristics in various media as well as in a vacuum. When light goes from a vacuum to some medium, like water for example, the speed and wavelength will change, but the funny thing is the frequency, which is f, will stay the same. I mean, for the medium to change, but then the wavelength to stay the same, that is sort of mysterious. We're not sure how light controls that. And in conclusion, interference determines the outcome of every photon or wave-like experiment. So light interference, it changes again. Will the frequency stay the same depending on the experiment that you're running? And what are you going to conclude? Are you going to find wave or particles, depending on what experiment you're using and what it is that you're looking for if you're trying to discover the nature of light by refraction, reflection, or via the double slit experiment. So, one scientist concludes, what is light? Does light switch from being a particle to being a wave depending on the circumstance? Or is light always both a particle and a wave simultaneously? And to this day, scientists aren't sure. They don't know. But right now, they are working on a third slit theory to see if they can find a third nature about light. But for now, we know conclusively that light is both a particle and also a wave. Again, my name is Nicola Hines, and I hope you enjoy my summary. Have a great day.